we will now move on to rational functions. So, polynomials of higher degree, gone. And instead, we'll do fractions, because we know how much we all love fractions, right? Fractions is everybody's favorite, isn't it? Yes? See? One person's honest. No? Nah, liar. Everybody loves fractions. Okay, so anyway, graphs of rational functions is what we're going to be doing. And we'll be studying rational functions for the rest of the chapter, talking about solving them, graphing them, using them, all kinds of good stuff. So what is a rational function? Well, basically, a rational function is any function that has x's in the denominator. Boom, there it is. Now, normally you'll have polynomials on the top and the bottom, so x is in the top and the bottom. But basically, you have x's in the denominator of a fraction, rational function. That's what's up. Obviously, the denominator is never allowed to equal 0. That's always going to be a truth. So this first question asks us to find the domain of 1 over x minus 2, and then we're going to use limits to describe the behavior as we get close to the number that is not in its domain. What is the one value that x cannot equal? Lots of people. What's the value x can't equal? 2. X can't be 2 because the bottom of the fraction would then be a 0. So our domain, oh, look, that's green. Well, oh well, we're already there. Is negative infinity to 2, union 2 to infinity. Boom, there it is. Domain. It's any number except for the number x equals 2. Let me switch over to blue because I like that better. So what we've been asked to do now is use limits to describe what this graph is doing around the value x equals 3. And I'm going to use some symbols that I don't think you've ever seen me use before, but that's okay. I'll explain them as we go. So we're going to be finding the limit of the y values, meaning what will the y values be doing as x gets close to the number 2. But specifically, I'm going to approach the number 2 from the left of it. So 1.9, 1.99, 1.9999999. The point is, I'm going to be getting really, really close to x equals 2, but just to the left of x equals 2. So those symbols, again, that symbol says, hey, what are the y values doing as x gets close to 2, but from the left of 2? So what are the y values doing? Well, we can figure this out without graphing it. And we just do that by big braining our way there. So let's just pretend we're going to plug in the number 1.9999999 right there. What do you know about the denominator of that fraction then if you are plugging in 1.9999999? What do you know? We know two things. If I plug in a number that's just smaller than 2 about this denominator, there's two things we know. It's less than 0, which means it's negative. Okay, so if we plug in a number that's ridiculously close to 2, but just a hair smaller than 2, the bottom of our fraction is now negative. And if I'm plugging in a number that's ridiculously close to 2, and then I'm subtracting 2, the other thing we know, the bottom of that fraction is very, very small, really small. And if you were to take a number, like the number 1, and divide it by something incredibly small, what happens to it? When you divide by things that are incredibly small, it becomes bigger. In fact, it's going to get so big, it's going to approach infinity. So the closer we can get to 2 from the left side, the smaller the denominator would be. So 1 divided by incredibly small approaches infinity. However, remember we just found out that if we plugged in 1.9999999, the bottom is negative. So we're approaching negative infinity. That means as I get really close to x equals 2, my graph shoots down towards negative infinity. And we can approach x from the other side as well. So you go, okay, I want to know what my y values are doing as my x values get really close to 2, but they always stay just a hair to the right of 2. So a number like 2.001, lots of zeros, and then there's a 1 at the end of it. You plug that in. What are the two things you know about the denominator of the fraction now? Come on, 2.0000001 minus 2. What do we know? It's greater than 0, so positive, and it's still ridiculously small. So we are now dealing with a positive number on the bottom. It's already a 1 on the top. So we have 1 divided by something positive, and that something positive is ridiculously small. So again, 1 divided by ridiculously small, infinity. But this one's positive. So what that says is, just to the right of the number x equals 2, my graph should be shooting up towards infinity. A couple basic little rules for you. Let's see where I can squeeze these things. I think I can get it right here. Works like this. Constant over stupid small is essentially going to be infinity. And constant over ridiculously big if I take a constant and I divide it by something outrageously large, what is that essentially equal to? Well, let's think about it. Let's say I had $1 and all 7.5 billion people in this world had to split that $1. How much would we essentially get? Nothing, 0. So constant divided by gigantic is essentially 0. Constant divided by incredibly small is essentially infinity. There we go. Of course, that's what happens when you do limits. Because you're allowing, for the first fraction, you're allowing the bottom to get smaller and smaller and smaller, which is allowing the value to grow and grow and grow. And the opposite is true for the other fraction. As the bottom of that fraction gets bigger and bigger and bigger, the value of our fraction comes down and down and down, approaching 0. All right, well, speaking of just to the left of a number going down to negative infinity and just to the right of a number going up to positive infinity, I give you the parent reciprocal function, the parent rational function. F of x equals 1 over x. Its domain is going to be everything except for the number x equals 0, because you can't divide by 0, right? And because it's a positive number divided by another positive number or divided by another negative number, guess what the value of the fraction will never be? 0. So it has a horizontal asymptote at y equals 0. So 0 is not in my domain or my range. It's continuous everywhere except for x equals 0. It's decreasing to the left of the y-axis. I said that backwards. It's decreasing everywhere. I'll be okay. It's decreasing everywhere. I'll be fine. Whew. Had a brain fart for a second there. It's unbounded, clearly. It's got no local extrema. I've already mentioned the horizontal vertical asymptotes. We've already seen the in behavior. Most important thing in this box is this. Standard form. H, K, and A are all transformations on that parent function. A would just be changing the number like from a 1 to a 2 or a 3 or something like that. That A number on top would be your vertical stretch or shrink. It would also represent reflections. So if that number is negative, that is a reflection over the x-axis. Oh, by the way, I skipped right over for some reason, but this thing has odd symmetry. Reflecting over the x is the same as reflecting over the y. All right, well, you know you can't divide by 0, right? So this number right here, that will always be your vertical asymptote, the number that makes the bottom 0. And since this thing is supposed to have a horizontal asymptote at the y-axis, shifting it up or down would move that horizontal asymptote. So this number will always be the horizontal asymptote. We cool with those two ideas? Okay. Oh, I'm popular, getting a phone call. Alrighty, we good? Ready to do some stuff? All right, let's come on down. Got two different graphs going on here. I'm going to deviate from the directions a little bit just because I'm going to focus on the stuff I want to do rather than the stuff the book wants me to do. It says to describe how the graph of the given function ka be obtained, clearly there's an n missing there, can be obtained by transforming the graph of the reciprocal function 1 over x. So we just want to know, how do we get this function from the parent function. Cool. What are we going to do after that? Identify horizontal vertical asymptotes, use limits to describe the behavior, sketch the graph. I'm going to skip over the using the limits to describe the behavior stuff. Instead, we're just going to go directly to sketching the graph, if you're okay with it. We all right with that? So we're going to describe the transformations. Well, the top of the fraction is supposed to be a 1. Right now, it's a 2. So what kind of transformation is that? Yeah, vertical stretch, specifically factor 2. Vertical stretch, factor 2. The board is lagging very badly. The bottom is supposed to be just an x. I now see an x plus 3. What is that? Yeah, left 3 units. We're shift left 3 units. Wow, this is painfully lagging. Shift left 3 units. Great. You see, I didn't shift up or down, right? Since we didn't shift up or down, this is going to have the same horizontal asymptote as the parent function. That horizontal asymptote will be the x-axis, which is y equals 0. However, our vertical asymptote, which was supposed to be the y-axis at x equals 0, has been shifted left 3. Or you could just say, well, I see a negative 3 is not allowed to be plugged in. So my vertical asymptote is at x equals negative 3. And let's just go ahead and sketch the graph. There's negative 3, vertical asymptote. X-axis, still the horizontal asymptote. The parent function has its curves in the top right and the bottom left. Did we reflect this at all? Since we didn't reflect it, it will still exist in the top right and the bottom left. So to say it like that, instead of using limits, because yuck, we're not in calculus yet. Let's just do it like that. Okay. That was pretty easy, right? So we'll just look to that second one and we'll see what kind of transformations we... Oh boy. Okay. There's x's on the top. That's not a transformation. So what we're going to have to do is we're going to have to get this rational function into standard form so we can actually see which transformations have happened. And that is going to require long division. It's not hard. Don't worry about it. It's actually really easy. It's very simple, I promise. Our job is to make that x become the 3x. Remember, we have to make the fronts match. So what do I have to multiply by? 3. Yeah, okay. So I'll just put that 3 right here and, ooh, I didn't want to use black. Put that, come on, active panel, catch up. You can do it. Come on. It flashed like it did something, but it did absolutely nothing. Great, we're crashing. Yay, all right. I feel like that only happens in your class. So we're going to take this 3, we're going to distribute it to the x minus 2. It's going to give us 3x minus 6. Lag so hard that it looks like a caveman chiseled it. Let's try. I'll write slower. Subtract straight down. Watch your double negatives. What you're going to get there is a remainder of negative 1. But instead of writing minus 1 over x minus 2, I want to write it as plus and do negative 1 over x minus 2. And guess what? That is dangerously close to being standard form. It's just written in the wrong order. There. It's standard form, and we can see the transformations that have been performed. Looks like 1, 2, 3 transformations to me. See, everybody heard long division and got a little worried, but it wasn't hard at all, right? I mean, that was pretty simple. Okay, let's describe those three transformations. What's that negative sign? It's a reflection of some sort. You know what's great about odd functions? It doesn't matter if you say reflect over x or reflect over y. It doesn't matter because it's odd. But technically, because it's an outside change, quote unquote, because now the inside is where the x's are, which is the bottom, we're going to call that a reflect over the x-axis. And where am I going to squeeze this in? I'll put them over here. Reflect, oh my gosh, this board. Holy cow, this is so bad. Reflect over x-axis. It doesn't matter which of the two shifts you describe first, because one's an x and one's a y. So let's just keep working the fraction. What is the -2 going to do to the graph? Yep, shift right 2 units. And then the +3? Yeah, shift up 3, good. You know lots of you are allowed to talk to me, right? I like when lots of people speak. Okay, well, we can use that knowledge to figure out where our asymptotes are. We said that we have shifted to the right 2. Well, that vertical asymptote that should have been at x = 0 is now at x = 2. And the horizontal asymptote, which should have been at y = 0, has been shifted up 3. And we do know that there's been a reflection. Since there has been a reflection, the curves will not exist in the top right and bottom left. They'll switch places. See where I can fit this graph. Yeah, I got space right there. Cool. 2 and 3. And like I said, not top right, bottom left because of the reflection, the other way. There you go. That's good enough. Not bad, right? Not scary at all. Of course, if you have any questions, let me hear them, please. No? All right. Nope. No Gavin in 8th period. What's my favorite class to teach? You mean period or material? My favorite material to teach when I get to is calculus. So I teach that to my IB students and I teach it to you guys. So behind calculus, my favorite material to teach is trig. I love trigonometry. Absolutely love it. All right, let's find some asymptotes. We are supposed to find the horizontal and vertical asymptotes of that f of x. Nobody likes side-to-side fractions, so I'm going to start by writing this thing as a stacked fraction. X squared plus 2 divided by x squared plus 1. Let's go after the low-hanging fruit, the easy part. Easy part is always going to be finding whatever makes the denominator equal 0. So we're going to look up here to x squared plus 1, and I'm going to ask you, what makes that denominator equal 0? Oh, plus or minus I? Oh, those are complex numbers. Yeah, we can't graph those in the standard number system. So what does it tell you? It doesn't have, well, no, that doesn't say that. It tells you that it doesn't have any vertical asymptotes. Since the bottom of this fraction can never equal 0, it doesn't have a vertical asymptote. Simply doesn't. X squared is always going to be a positive number. There's no way you could take a positive number, add 1 to it, and get 0. So there you go. Yeah, no vertical asymptotes. But it does have a horizontal asymptote. And we learned about this earlier in the year, but we might as well recap. The rule that I taught you was when the degree of the top is equal to the degree of the bottom, the horizontal asymptote is always going to be the leading coefficient divided by the leading coefficient. Our leading coefficients are 1, both of them, 1 and 1. So this horizontal asymptote is at y = 1. we've been asked to use limits to describe the corresponding behavior. Well, the definition of a horizontal asymptote is what the graph is doing at the two infinities, at both sides, positive and negative infinity. So without even using limits, we know that the limit as x approaches negative infinity is equal to the limit as x approaches positive infinity is equal to 1. That's kind of the definition. I mean, I'll write it, but so the limit as x goes to negative infinity of our y values is the same as the limit as, come on board, x goes to positive infinity of our y values. And yeah, it's equal to 1, the horizontal asymptote. What's that? What would that graph look like? What a wonderful question, because I know it's not asked, but I was going to draw it anyway. What a good question. What does that graph look like? Well, first of all, notice that the top and bottom both have x squareds in them and no other x's. What does it instantly tell you about the function? Come on, guys. Get there. Come on. All the exponents are even. It's an even polynomial, or an even function. It's going to be symmetric over the x-axis, or over the y-axis. You guys let me down on that one. Alrighty, well, we know at x equals 1, we have a horizontal asymptote, which means we know we're going to approach that line at both infinities. See how the denominator is 1 less than the numerator? Because it's a plus 2 on the top and a plus 1 on the bottom. What that tells us is that the top of this fraction will always be bigger than the bottom. So that tells us that every one of its values will be larger than 1. So the entire graph exists above this horizontal asymptote. We know what's happening at the infinities. Why don't we talk about what's happening at the small values of x, like 0? Let's plug in x equals 0 and see what we get. Oh, we get 2 over 1, which is 2. This graph looks like this. There you go, just like that. Doesn't have a choice. The further away it gets from x equals 0, the closer it's going to get to y equals 1. Pretty easy, right? Of course, you weren't asked to do that, but that's what it would look like. And like I said, symmetric over the y-axis, even function. Yes, sir? Well, we knew that because the top is 1 bigger than the bottom, we knew that no matter what we plugged in, the top is always larger than the bottom, which means the entire graph has to exist above the line y equals 1. Okay. And we know it's an even function, or I keep saying, yeah, function. We know it's an even function because both of the exponents are even. So plugging in negative x would have done absolutely nothing to it. And you know it has to get close to that red dotted line. That's the definition of a horizontal asymptote. So on both sides, you had to get close to that. And in the middle, I just plugged in x equals 0. So we really didn't have a choice. It was going to look like that no matter what we did. Mm-hmm. Big old box of information. A graph of it, what? Somebody panic? Should I go back up? Graph of a rational function has these characteristics. First of all, I am no longer going to say horizontal asymptote. Instead, what I'm going to say is end behavior asymptote. Because a horizontal asymptote is an end behavior asymptote. A slant asymptote, also known as oblique, is an end behavior asymptote. And then there are other end behavior asymptotes that are polynomial in nature, but they're all end behavior asymptotes. From now on, they will be henceforth known as EBA, end behavior asymptote. Yes, ma'am. Yeah. So recap of the rules that we talked about earlier in the year. If the degree of the top is less than the degree of the bottom, automatically the x-axis is your horizontal asymptote, which is its end behavior asymptote, automatically. Reason why is because it would behave the same way as constant over infinity. Like if you had x over x squared, that would reduce to 1 over x. So if the degree of the bottom, if the degree of the top is smaller than the degree of the bottom, automatically y equals 0, horizontal asymptote, end behavior asymptote. if the degree of the top and the bottom are equal, leading coefficient over leading coefficient, still a horizontal line in behavior asymptote. But what if the degree of the top is larger than the degree of the bottom? Well, if it's only one larger, then you're going to have a linear asymptote, oblique asymptote, slant asymptote. It won't be horizontal anymore, it'll have slope. Okay? But that's specifically if the degree of the top is 1 bigger than the degree of the bottom. If it's more than 1 bigger, then your in-behavior asymptote will be polynomial in nature. You could have an x to the third in-behavior asymptote. Just means that at the infinities, the graph would look like that polynomial. Doesn't tell you what's going on when x is small, but at the infinities, it would look like the polynomial. And we find those polynomial in-behavior asymptotes by using long division. That's how we find those. You guys okay with that idea? So we're going to do it in a minute. Vertical asymptotes, yeah, that's anywhere where the bottom is going to be equal to 0 if it happens. X-intercepts, that just means you're on the x-axis. So that's where y equals 0. And y-intercept, not intercepts. You can't have more than one, because if you did, you have something that's not a function, because it fails the vertical line test. So the y-intercept is very, very easy. You just plug in x equals 0. Plug in x equals 0, you'll be able to figure out where any graph crosses the y-axis if it crosses the y-axis. And of course, these things are as long as 0 is not in the, as long as 0 is in the domain. I mean, if you plug in 0 and you break the rules, well, like the reciprocal function, it doesn't cross the y-axis because x can't equal 0. So let's graph us one of these bad boys. First of all, stacked fraction. We don't want it to be side by side. It's hard to look at. What do you guys notice about that x squared minus 9? Ah, it's the difference of 2 squares. So we can factor that, and we should, because that will show us where our vertical asymptotes are. There. Cool. We can see the vertical asymptotes very easily. They happen at x equals -3 and x equals +3. All right, all right, all right. Now what I need is my in-behavior asymptotes. In-behavior asymptote. Ah, yeah, the degree of the top is 1 more than the degree of the bottom. If you don't want to remember that that's going to create a straight line asymptote, a linear asymptote, or slant or oblique, however you want to say it, then just do some long division and see what you get, because that will be the in-behavior asymptote. So yeah, I'm going to do a little bit of long division to find my EBA. I'm divided by x squared minus 9. Technically, I should be writing x squared plus 0x minus 9. So I'm just going to go ahead and do that. Be a good mathematician. And I'm trying to make this become an x to the third. Okay. Well, let's see what we're going to get. What do I have to multiply that x squared by to make it look like an x to the third? Oh, an x. How about that? Okay. X. Now let me distribute that x and see what we get. We get an x to the third plus 0x squared. Okay, well, let's just go ahead and throw a 0x squared above it. Minus 9x. Let's throw a 0x above it. Extend our fraction bar. There we go. Or not fraction bar, but our division symbol. And let's subtract straight down and see what we get. X cubed minus x cubed, 0. 0x squared minus 0x squared, 0. 0 minus negative 9x, positive 9x. Oh, and that will be my remainder. How do I recognize that as my remainder? Well, because its degree, 1, is less than the degree of the divisor. Come on, active panel, catch up with me. Oh, good, we're crashing again. All right. So this gives us x, in behavior asymptote of y equals x, plus this little deal. And you might be wondering to yourself, but what am I supposed to do with that? And I go, remember, we're modeling what's happening at the far infinities. At the far, far infinities. So let me ask you a question. At the far, far infinities, does that minus 9 mean much? No. So at the far, far infinity, you could just kind of ignore the minus 9. So now you'd have 9x over x squared, which reduces to 9 over x, correct? And remember, we're talking about the far, far infinities. So 9 over ridiculously big would essentially be equal to something, a constant over ridiculously big gives you a 0. So essentially, at the infinities, this just equals x. So your in behavior asymptote is y equals x. See, the little fraction remainder is not ever going to matter because the little fraction remainder will always have a smaller degree on the top than it does on the bottom. That means at the far infinities, the little fraction remainder will always go to 0, and it will not be a problem. Will every linear or oblique or slant asymptote be y equals x? No, it could have been y equals x plus 2 or something, okay? This one just happens to be y equals x. Let's get ourselves a sketch. Let's see. We have a problem at positive 3 and negative 3. And it's not that it's a problem, but the line y equals x models our end behavior, what it looks like to the far left and the far right. It's like that. Okay. I think it's important that we at least show the coordinates of this intersection of asymptotes. That happens when x is 3, correct? And the oblique asymptote is y equals x, right? So this is also happening at y equals 3. You'll see why in a minute. And by the same logic down here, this is happening at negative 3. There. Just so we know. Time to start sketching. Well, I'm going to be real. You're just going to have to plug in some values. What's a really, really, really easy x value to plug in? 0 is where I would start, and then I'll go to 1. But we'll start at 0. If we plug in 0, we get 0 over negative 9. So at x equals 0, y equals 0. Does it bother you that this graph exists on that slanted dotted line? You see, somewhere along the line, you might have gotten into your head that an asymptote is a line you cannot cross. No. An asymptote is a line you approach. This one's called an end behavior asymptote, which tells you your graph will get close to this at its edges, not when x is small. So that slanted line, that's what your x's will be behaving as when x is positive infinity and when x is negative infinity. What's going on at 0 is whatever the heck wants to go on at 0. Okay? So now let's figure out what else it's doing between the two vertical asymptotes. Let's plug in positive 1. Let's plug in negative 1. I mean, do I have space down here? I have space down here. Let's see what f of 1 is. F of 1 gives me 1 over 1 minus 9. That's negative 1/8. I'm not going to try to plot that. What I do know, though, is as I go to the right and head towards that vertical asymptote, and remember, you have to get close to that asymptote, my y values turn to negative. So as I move to the right, my y values turn to negative. Let's see what happens as we move to the left. Let's plug in negative 1. The top is x to the third, so it's negative 1. But the bottom's x squared, so it's still 1 minus 9. That gives me negative 1 over negative 8, which is positive 1/8. Again, I'm not going to try to plot this. The point is, as I move to the left, and remember, I'm going to have to get close to that asymptote. As I move to the left, I ended up with positive y values. What shape does that look like? A cubic. Oh, look, a cubic. So I'm not surprised. Now we need to do those. We need to figure out what's going on to the right of 3 and to the left of -3. That's what we need. So again, I would have just tested values. So you could plug in the number x equals 4, right? And when you plug in x equals 4, just so we're all clear on this, if this is x equals 4, it hits that slant asymptote at y equals 4 because, y equals x. All right? So this point is 4, 4. We cool with that? Great. Let's plug in x equals 4. Scroll down again. F of 4. 4 cubed divided by 4 squared minus 9. 64 over 7. Look, I'm not going to try to plot 64 over 7. You know the only thing I care about? It's bigger than 4. 64 divided by 7 is larger than 4, right? So that means at x equals 4, I exist above this red dot. So that curve up there does this. And you could plug in x equals -4 if you'd like to. But I would like you to use a little bit of brain power here. If I plug in a -x, will the bottom change? But if I plug in a -x, will the top change? Isn't that the same as multiplying the entire fraction by -1? Yes. Oh, this is an odd function. It has odd symmetry. That forces the other piece of that curve to be down here. And if you're not comfortable with that, by all means, let us plug in the number -4. -4 cubed is -64. But on the bottom, I'm still going to get 16 minus 9. This is -64 divided by 7. And remember, this red dot happens when x is -4. And y is also -4. I don't care what the value of -64 over 7 is. All I care is that I know it is less than -4. And that's why that curve exists below this red dot right here. Oh, I'm coloring it in blue, but you get the idea. And that's enough for today.